Today we are going to discuss what is known as generation of random variates. We have seen in our previous examples that the random numbers are coming from uniform distribution, but most often for the purpose of simulation it is not sufficient that we have the uniformly distributed random variables, because the particular things, for example arrivals or service etc., they are all coming from some other distribution. So, how to convert those random numbers into the random variates or the random variables coming out from a given distribution, that is what is required. So, a random variate is an artificially generated random variable, right. Input variables for simulation follows some specified probability distribution. To generate some samples from a given distribution, random numbers are drawn, right. So, let f x be the cumulative density function of the input variable and r is a random number. So, exactly let us look at, suppose we want a random variate for exponential distribution. We shall look at the mathematics a little later, but let us look at the exponential distribution, how it looks. This is usually the what is known as the f x, right, the probability density function. So, what would be the right, then that will be the cumulative distribution function. So, this is PDF and this is CDF, probability distribution, and this is CDF. Now, fortunately for us, this is 0 and this is 1. So, if you really look at the CDF, and this side is x, right. So, what you can do if this number is between 0 and 1, now see, you can take a random number between 0 and 1, and let us say your random number is this. So, a random number r which is between 0 and 1 is taken, and this random number, if you project it onto the particular distribution, then we get an value of x. So, you see, this is r is a random number and this x is a random variate. And this is an for exponential distribution. So, this is a random variate for exponential distribution. Now, mathematically speaking, r equal to f x. So, x equal to f inverse r, right. So, this is called the inverse transform method, right. That is why it is called inverse transform method. All right. So, we have the probability density function, we have the cumulative distribution function, and after that if we take a random, but this will be between 0 and 1. So, if we take a random number, we know a random number is also between 0 and 1, that random number can be projected onto the cumulative distribution function, and that corresponding x value would be the random variate. Essentially, what are you doing? We are transforming the random number into a random variate from a given distribution. That is what the inverse transform method actually does. right. So, if r equal to f x, x equal to f inverse r, that is the method. There are other methods, but let us see this method first. So, you see that is exactly what I told so far is here, where r is a random number, capital F x is the cumulative distribution or density function, and then x is the random variate. So, what happens in exponential distribution? In exponential distribution, what is the value of f t, right? The value of f t equal to, or even f x you can write, because here we are writing x. So, let us write x also, it is lambda e to the power minus lambda x. So, what will be capital F x? The cumulative density function, it will be 1 minus e to the power minus lambda x, right. So, that is our cumulative distribution function. So, if you equate this to r, so what will happen then? You can write down e to the power minus lambda x equal to 1 minus r, right, 1 minus r. So, this is the equation that we can use. We can see further how we can exploit this particular equation, right. So, exactly that is written here, the average is 1 by lambda. To obtain the number of exponentially distribution random numbers, the CDF f can be equated with u or r as the case may be. So, as generated uniform random number, so exponential random variate is f inverse u. Now, in this case, since u equal to f t equal to 1 minus e to the power minus lambda t in this case, so minus lambda t is ln 1 minus u, right, and therefore, t will be minus ln 1 minus mu by lambda. In our case, look at what we can get, it will be x equal to 1 by lambda ln 1 minus r. Okay. Now, there is a minus sign, right. Now, one thing is look here, that should we use 1 minus r? What is 1 minus r? Basically, there is a random number r. So, a random number is between 0 to 1. So, if r is a random number, 1 minus r is also another random number. We might call it r dash, or you call the original one as r dash and 1 minus r as r, right. 1 minus r dash equal to r is also a random number, right. So, using that fact, we can write random variate x equal to minus 1 by lambda ln r. Okay. So, that is how we can actually get a random variate from an exponential distribution, right. So, that is exactly, if you look at that a particular one, that is t equal to minus ln 1 minus u by lambda, or t equal to minus ln u by lambda, and thus exponential random variate t k equal to minus ln u k by lambda. So, this is how we can actually compute an exponential random variate, right. So, suppose, let us go one step further. Suppose we have two random numbers, let us say 55 and 78. What we have to do? We have to convert them to, these are two random numbers, and suppose we have to generate an exponential inter-arrival time. So, we have to convert them to random numbers between 0 to 1, 0.55 and 0.78, and suppose lambda equal to 5 per hour. All right. So, two random variates will be for exponential distribution. Inter-arrival times would be generated as x 1 equal to minus 1 by 5 ln 0.55. Mind you, ln 0.55 is a negative number. So, that negative and negative will make it positive, and x 2 will be minus 1 by 5 ln 0.78. Is it all right? So, this is precisely what we have to do to generate a random variate from an exponential distribution. Sometimes we may not get an distribution as a something like exponential and all that. Suppose we have got a random variable x with the following probability density function f x equal to 2x square. So, what would be its random variate? You see, interestingly, what we have to do? We have to compute if f x equal to 2x is 2x, then we have to compute the cumulative density function f x, which would be how much? It will be 2 f x is 2x square, it will be 2x cube by 3, right, because that will be then integration. So, that integration would result 2x cube by 3. So, if we want a random variate and if we then equate random number. So, uniformly distributed random number r is taken. So, r equal to f x, that is the inverse transform 2x cube by 3, right. So, from here we get x cube equal to 3 r or x equal to that is what we shall get, right, the 3 r by 2, right. So, this is going to be our random variate for the given distribution, right. So, you see, if you have a function which is not something like an exponential distribution, so we have to find out what is known as the cumulative distribution function CDF, equate it to r, capital R, that is the random number, and from there find out the given value of the random variate. Here is one more example. Consider a random variable x with the following probability density function, that is f x is x for 0, that is 0 to x to 1, 2 minus x for between 1 to 2, and it is 0 otherwise. So, find its random variate, right. So, what we have to do? We have to obtain for each by an integration process what is the CDF. The CDF will be therefore f x equal to 0 for x less than equal to 0, f x equal to x square by 2 for 0 to x less than equal to 1, and capital F x equal to 1 minus 2 minus x whole square by 2 for 1 between x and 2, right, and let us say capital F x equal to 1 for x greater than equal to 2. So, when you have all these cumulative density functions, and then if we equate, then we find for the first case when it is between 0 to 1, then r equal to x square by 2, and when we get between 1 to 2, r will be 1 minus 2 minus x whole square by 2. So, we get therefore, random variate x will be generated by root over 2 r for between 0 to r to half, but if the random number is between half to 1, then x will be 2 minus root over 2 into 1 minus r. So, you see if the distribution is different for different range, we may have to use different formula depending on the kind of probability distribution function that we have at a given point of time, right. So, the random variate generation therefore could be rather involved at different points of time. We shall now take a slightly complicated case that is known as the normal random variate. You see, the normal distribution is some very important distribution, and if something is normally distributed, we actually may have to have a normal variate for our calculations. So, in order to do that, consider two standard normal variables z1 and z2 plotted as a point in the plane as shown below. So, what happens that two standard normal variates z1 and z2, usually what happens, if they are orthogonal to each other, then they will be in two different axis directions, and they might have what is known as a particular intercept on various there on the polar coordinates, and in terms of polar coordinates they can be represented in terms of capital B and theta, and we might show z1 equal to b cos theta and z2 equal to b sin theta. So, once we have that, we can therefore write the b can be generated as minus 2 ln r to the power half, right. So, because b square equal to z1 square plus z2 square, normally it can be seen that if they are standard normal variables, then b tends to follow what is known as chi-square distribution. So, by the symmetry of the normal distribution, we can assume that the angle is symmetrically distributed between 0 to 2 pi radians, and also radius b and angle theta are mutually independent. So, through that what we can do, we can actually write z1 and z2 by z1 equal to minus 2 ln r1 to the power half cos 2 pi r2 and z2 equal to minus 2 ln r1 to the power half sin 2 pi r2. So, you see, forgetting the complications of the mathematics that is presented here, these two relationships are very important, because if we have two random numbers r1 and r2, by these transformation we can actually generate two normal variates, right. So, suppose it is said, just for the sake of this, let us assume that arrival and service are both normally distributed. What we have to do? We have to really obtain two random numbers, one for arrival, one for service, and we can actually generate two normal variates minus 2 ln r1 to the power half cos 2 pi r2 and minus 2 ln r1 sin 2 pi r2. So, two normal variates can be obtained from this particular distribution, right. Now, let us look at what is known as Erlang random variate. This Erlang random variate we have not discussed while we discussed the queuing kind of thing, but this is a very important distribution, and particularly it happens when we have k independent exponential random variates, right. Supposing there are a large number of servers and all the servers are serving in an exponential manner. What you can do? You can do an Erlang estimation and replace all the servers by a single server and then make it simple, right. So, that way you can aggregate the service process by the Erlang assumption, right. So, if there are k independent exponential random variables, then a sum of all of them really is an Erlang distribution. So, how exactly it is possible to obtain an Erlang distribution function? That is, what we have to do, we have to really come up with the individual exponential distribution and then sum over them, right. And the distribution x in this case would be the sum of all the distributions, that means all the individual exponential distributions, and from 0 to k, because there are k independent exponential distribution which are summed here. And then what we have to do, we have to find out the if they are all identical, then each of them will have a random variate which will be governed by this 1 by lambda, in this case k lambda, because we are having, each is having a mean of 1 by k lambda. So, 1 by k lambda minus ln r I, is not, and then when you sum them up, sum them up all, then you get an Erlang random variate, that is I equal to 0 to k minus 1 by k lambda ln r I. So, that would be our Erlang random variate, and this Erlang random variate can also be expressed in this form minus 1 by k lambda, because it is a constant, it can be taken out, then it becomes sum of ln r I, but we know that ln, it is basically then ln r 1 plus ln r 2 plus r 3 etc. But then we know that sum of this ln is nothing but ln r 1 into r 2 into r 3 into r 4. So, there is that multiplication symbol could be shown in this form. So, it finally becomes minus 1 k lambda ln r 1 into r 2 into r 3 up to r k, right. So, in this form it becomes simplest, and that would be an Erlang variate. What is the advantage we get out of this? Suppose we know that there are k independent exponential random variables, all of these things are happening simultaneously. Assume that people are arriving at a particular railway station. Now, while people are arriving at the railway stations, all types of people are arriving, is it not? Assume that there are some office goers who are coming back for train, there are some vendors, they are coming from train, there are some what you call maybe the students who are coming for train, and if we know they are essentially they are all different independent exponential distribution, then all of these can be summed up together and an Erlang random variable can be used as an their sum. Now, let us look at another method which is known as the rejection method. The rejection method is so basically there are 3 ways, in fact there are 4 ways random variates can be obtained. What are those 4 ways random variates can be obtained? 4 ways can be obtained. If we want an uniformly distributed random variate, use random numbers directly, right, use random numbers directly. Second, random variate from a distribution not known but values are associated with probabilities. So, like we have done the queuing problem example, right. So, random variate from a distribution not known, but values are associated with probabilities. So, what we can do? Allocate random numbers to specific values. So, this we have seen in the queuing examples, right? Allocate random numbers to specific values. The third is the inverse transform method. The inverse transform method basically r equal to f x. From here x equal to f inverse r. What happens? The f x is known. That means the cumulative distribution function is specifically known and that can be used. The fourth is the rejection method. That is what we are discussing now. Basically, here also the f x may be known, not really. Only thing we have the values and we can actually draw the probability distribution function, but then it is not that all the random numbers that we have may not be possible to allocate. So, what happens? We may have to reject some random numbers and we have to keep the remaining random numbers from a given distribution. That is what is a rejection method. So, a rejection method for obtaining sample works by generating uniformly distributed random numbers repeatedly and accepting only those numbers that fulfill a given condition. The condition of acceptance need to be designed such that the accepted numbers appears to be drawn from the given distribution. For the rejection method to be applicable, the probability density function of the distribution must be non-zero only over a finite interval p q. Let f t be bounded by an upper limit r. So, here that is the the diagram. So, what happens? That this is the function, and in this function what happens? We have the function is bounded by one value a, another value b, and let us say p is a number which is in between a and b and can be written as a plus b minus a u1, where u1 is a random number, right. So, let us take two random numbers u1 and u2 over the interval 0 1, right. So, what you can always do? You can use E2 locate point P on the horizontal, using u1, this is wrongly written. So, we have corrected it using u1 locate point P on the horizontal axis, that is P equal to a plus b minus a into u1, right. So, this is the point P. Using u2 locate a point Q on the vertical axis, Q equal to C2. So, if we have those 2 points and if Q is greater than Fp, then reject the pair and go to step 1, else accept P as the value of a sample from the desired distribution. So, see what is really happening, then you are generating 2 points, that is P and Q, and then you are seeing whether that point is, see this point, suppose the Q is here, right. If the Q is here, then we get this point here, which is outside the function. This is the function between a and b. This, if we hatch this portion, then this is where the function is. But if the point is beyond this fx ft, then reject the point, otherwise accept the point. So, that is the essential idea, and this method works only for a finite interval. So, that is what is a rejection method, and if the function is such that we really do not have any specific set of equations, but we have a plot, then we can also find a random variate from this particular method, right. We stop here, and in our next class we shall see some more examples, and we shall then discuss some of the very important things about simulation, like validation, verification, and further how length of a simulation run can be obtained, how the input can be modeled, and how the output we can have confidence on, right. So, thank you very much.